Hello, welcome to Math. Today in this video, we'll be looking at how this problem here can be solved using substitution and DI method. Using substitution and DI method. The question here is an integration apart question. And with integration apart question, actually you differentiate one and you integrate one. But here we are going to first apply use substitution. Why? Because though it's an integration apart question, but you could see that the derivative of this can eliminate this one, and we can do that by what? Substitution. Only if we substitute another variable for this one, differentiate, whatever we get will be the same thing as this, which will what? Help eliminate this one. So because of the elimination that will include, or that we will come across in this question, or because of the elimination that we will come across, that is why use substitution has been included in the approaches going to be used. And also, after applying the DI method, you can see that there will be some parts where the DI method will not work again, where you have to, though the DI method will work, but actually it's not going to maybe it's not going to end for you. Okay, so maybe you have to stop somewhere, pick where you're going to further work on, and then continue from that place. So because of this reason, that is why we are going to use substitution approach and then DI hot method, so that where we have to use substitution, we just use it, and where we have to use DI method, we have to also where we have to use DI method, we just use it. Okay, so without wasting much time, let's see how these two approaches will help us solve this problem here, which is integral 2x multiplied by sine inverse of x squared dx. Integral 2x multiplied by sine inverse of x squared dx. So without wasting much time, let's get into the video. Let's write our solution first. What are we integrating? That is this one. So let's bring it down here. Okay, here we are going to do substitution. Remember I said though it's a integration apart question, it's an integration apart question, which we are supposed to use the traditional approach or the DI method directly from here. Okay, somebody can also use the integration apart approach, maybe directly from here, and get the final answer to this question. Maybe the experts, maybe, who knows, they can do that. But let's do it step by step. Let's work out the solution in bits. Okay, so first let's do substitution to eliminate what? This one. So we are going to let u be equal to x squared. We are going to let u be equal to x squared. So we let u be equal to x squared. Now let's differentiate. Now when you differentiate this one, we are going to get du, and when you differentiate this one, we are going to get 2 when you differentiate this one, we are going to get 2x dx. Now here we are going to divide both sides by 2x. We are going to divide both sides by 2x, all because we want to find what is going to replace what, dx. So let's isolate dx and know what is going to replace it. This and this will cancel out and to be left with this one. So dx is equal to 1 over 2x du. 1 over 2x du. Okay, here this one is equal to this and u is equal to x squared. So let's put them into the integral. 2x sine inverse of u multiplied by 1 over 2x du. Here, this one is here because of the cancellation. I want to show you the cancellation aspect. That's why I maintain it here. Okay, so here this one will cancel out with this one. It will be left with sine inverse of u. Here, to integrate this one, we have to apply the integration apart method, that is the traditional approach, or use the DI method. But here I'm going to use the DI method. Yes, I always prefer using the DI method because that one is very simple for me to use. Okay, both of them are simple for me to use, but I always prefer the DI method. It's, to me, is very simple and fast for me. Okay, so here we are going to use the DI method to um, solve this one. But with using the DI method, though, with the DI method, there has to be some two things. But here we are only having what, sine inverse of u. But though it's only sine inverse of u, but it's not only sine inverse of u. We will consider the coefficient of sine inverse of u, which is what, the 1. You could see that it's 1 times sine inverse of what, u. And because that one is there, it is making it an integration apart question. So using the DI method, we are going to differentiate 1 and then integrate 1. But here I'll differentiate sine inverse of u and then integrate 1. So let's put them into the DI format. Okay, let's put them. So as I was saying, so there is the 1, and also this is what the sine inverse of u that you were seeing. But this one is the coefficient of what, this one. So that one also we also have to what, work on that one also. Don't, yeah, if you treat it as constant, remember the other time I said if you take out the one, there is about billions of ones still there. Okay, so there is no need for you, taking it out. So let's work on it. Okay, here we are going to differentiate this one and then we integrate this one. Now when you differentiate sine inverse of u, we are going to get 1 over square root of 1 minus u squared. 1 over square root of 1 minus u squared. And when you integrate this one, we are going to get u. When you integrate this one, we are going to get u. Please don't write x for this one because we have moved from the x word into what, the u word. If you write x, you have to find another variable to replace it. Okay, so to be on the safer side, that is the world that we are in. You know that the question here was x squared, and now x squared has been substituted for what, u. So if you differentiate or integrate anything, whatever that you get should be in what, u world. Okay, after which maybe you go back. So when you integrate 1, we are going to get what, u. Good. With the DI method, the other time I said that with the DI method, there are three ways of using the DI method. Now, DI method is only used when you are solving maybe an integration apart. It's also another way of solving integration apart question. Apart from using the traditional approach, it's also a apart from using the traditional approach, this is also another way of solving integration apart question. Okay, so now with this format, the other time I said that there are three ways of using it. Maybe after you are done differentiating and maybe integrating about 2 or 3 rows, you just check the format. You just check what you have worked on. Just check what you have worked on, and maybe if check if you can, you know, get 0 in the D column, or maybe if the product of a row can be integrated or can be easily integrated, or if the product of a row gives the original question, which was which you were being asked to solve. So with the DI method, one, we stop when we get 0 in the D column, in the D, not here. Here, I don't think you will get 0 here. So the moment you get 0 in the D column, you just stopped, because when you multiply the product of a row, I mean where you had the 0, that row where you had the 0, when you multiply the 0 and what is under the integral column, you are going to get what? 0, and there will be nothing left to further what? Work on. That is why when you get 0 in the D column, we stop. 2, we stop when we realize that the product of a row can be integrated. Please, when I say the product of a row, don't go and just multiply this one. If you go and multiply this one, though it will give you the original question, but here you have done nothing. Is this the same thing as what? The first one. I said you consider the product of a row after maybe 1 or 2 maybe workings, after maybe 1 or 2 differentiating and then integrating. Okay, so we differentiate this one in the first, we differentiate this one and then we had this, we integrate this one and then we had this. And maybe if we press on, maybe integrate this one, whatever you are going to get, we write it here. Differentiate this one, we're going to, whatever we get, we just write it in the next row, maybe up to maybe about 4 rows. Then we realize that we have gotten 0 in the D column, we just stopped. Or maybe we realize that the product of a row, maybe the third row, we realize that when we multiply it, it gives the original question as what? Maybe this and that, which we are what? Maybe solving. It gives this one. That one too, we stop there. Or when we realize that the product of a row, we can easily integrate it without using DI method or traditional approach, but can be solved using other approach. Please, I said we stop when we get 0 in the D column, and also we stop when we realize that the product of a row, when I say product of a row, I mean when you multiply what is under the D column and by what is under what? The I column. When you multiply them, whatever you get is the product of what? That particular what? Row. So we stop when we realize that that product of a row gives the original question. And also we stop when we realize that the product of a row can be integrated without using the DI format or without using the traditional approach again, but with other approach, maybe partial fractions, maybe substitution, maybe the power rule or something else, maybe any other approach that can be used to solve the problem apart from either the DI method, apart from DI method or the traditional what approach. Okay, so here we are stopping, we are not going to continue using the format. We are stopping here because we can integrate the product of this and that using other approach. Okay, and also in writing your answers or in generating your answers from the DI format, we multiply the product of multiply the product of all the diagonals. The answers generated from the DI method are arrived by finding the product of what the diagonals. When I say the diagonals, with the diagonals, we just consider every row. Consider from row 1 to the very end. First one to the very end where you stopped. I said when you are writing your answers, you start from where you began to where you ended. Okay, so it is where we started, not here. We started by the positive first row where we wrote this and that. So if you are stopping here, the first part of our answer is what the product of what this and that, this and that. In using the format after writing this one, the subsequent rows is what we use to determine where we are going to stop. But in writing your answers, we consider the first row as part because of the product of the diagonals, which gives us the answers. Okay, so the first part of the answer for integral sine inverse of u du is from the DI method is the product of sine inverse of u and then u, so which is being indicated in the blue arrow. Okay, so this and this will give us the first answer to what that integral. So this is when you multiply this and this is what we are going to get. This is what part of the answer. And remember I said we are stopping because we can integrate the product of this and this, which is in red parenthesis, the product of all this and this using other approaches. Okay, and so when you multiply this and that, this is what you are going to get. Please mind you, when you are writing or generating your answers, make sure you consider the operation sign written along them. This plus is affecting the row of this negative is affecting the whole row. So assuming this sign inverse is negative itself, when you are multiplying, you consider this positive and that negative sign as well, and then you multiply with whatever that is. If this one too is negative, then it's going to be plus minus sine inverse of u multiplied by, if this one is negative, minus u. But if it is positive, then you are safe. You just take this one and this one, then you multiply. And when you do that, this is what you are going to get at the end of the day. Now, when you come here, you could see that this one is positive. This one is also positive. It is only the row that is what negative. But that does not mean when we multiply this and this, we are going to get what a positive answer, because the whole row is what negative. But if this one is negative and we multiply this by this, because the row itself is negative, it's going to be nege, which is what poor. But here we had minus integral u over square root of 1 minus u squared, because this and that is what positive and the row itself is negative. So when we multiply them, because they are still in the row, it makes it what negative. So we will just attach this negative sign to this one and then we multiply it with this, and that is what we are going to get at the end of the day. So there is integral u over square root of 1 minus u squared is what we are going to further work on. This one we are done but not done. But so far as integral sine inverse of u is concerned, this one we are done. This one is part of the answer, so we are done. But we are just left with this one. We are left to generate or get the answer for this one, of which we will add it back to this one, and then we get a whole answer for that integral. Okay, so let's work on this one to find out what we are going to get, and then we add it back to this one. Okay, here, because u is here and u squared is also here, we know that when we differentiate this, we can get this one. Okay, so we are going to do substitution. Of which whatever we get, we use it to eliminate what this u. So here we are going to do substitution. We will let m be equal to 1 minus u squared. We are choosing the whole thing because this one will just give us 0, and maybe this one will give us what you'll be looking for. Okay, so there's no need for us to make m be equal to this one alone. When you do that, just another the same thing but in different form. So to be on the safer side, we are going to let m be equal to this whole thing. Okay, good. Now let's differentiate. dm will be equal to minus 2u du. dm will be equal to minus 2u du. Now let's divide both sides by, let's find out what is going to replace du. Okay, so let's divide both sides by minus 2u. Here, this and this will cancel out, and this will also be cancelled out, and to be left with this. And so we are going to get du is equal to 1 over minus 2u dm. Okay, now we know what is replacing this. We also know what is replacing this. So let's put them into the integral. Good. Here we are having u here, and we are also having another u here. So this one and this one will cancel out, and to be left with 1 over square root of m multiplied by 1 over minus 2 dm. Now this minus 1 over minus 2 here is constant, so let's bring it out at the back of the integral sign. Okay, good. After bringing this one here, this is what we have gotten, 1 over square root of what? M. Now here, applying the negative index law of indices, this 1 over square root of m here can be written as, the law says that 1 over a can be written as a raised to the power minus 1. So applying this one here, we can write as m raised to the power minus half, or maybe square root of m raised to the power minus 1. Now when you write it, square root of m raised to the power minus 1, you are not wrong. When you do that, you have to rewrite it again to get this form. Okay, just that you have applied the law, all right, but the square root sign, you have to change it before you can integrate. Okay, if you don't change it, still you'll find it difficult. Okay, that is why I wrote it like this, straightforward. Minus half integral m raised to the power minus half dm. Now to integrate this one, you all know what we are going to do, the power rule. So we are going to add 1 to this power here, and then we divide the whole thing by minus half plus 1. Minus half plus 1. Please don't forget this constant. This one will multiply whatever we are going to get at the end of the day. Okay, so when we do that, minus half plus 1 will give us what now? 2 by 1 will give us 2. Minus 1 plus 2 give us what? That is the half here. The same thing is applied to the denominator. So that one also give us the same half. Here, these two will go and multiply this m raised to the power half. And that is going to give us minus 1 over 2 into bracket 2 m raised to the power half. And remember, m raised to the power half can also be written as square root of m. Okay, here let's open the bracket. Now when you open the bracket, you can see that this and this will cancel out and to be left with what? Minus 1. So minus 1 multiplied by square root of m will give us what? Square root of m. Now we are done with the integration. So what we are supposed to further work on after working on it, this is what we have gotten at the end of the day. But remember, we made substitution. So we have to, replace what we substituted this one for. Okay, so we know that m is equal to 1 minus u squared. Know that m is equal to 1 minus u squared. So let's put this one here. Sorry. Okay, good. Now here we are going to put the two answers together. Now because we are done with the integration of the question, we have to put our answers together to know what we are going to get at the end of the day. The DR method help us get part of the answer, and then also substitution approach in the other section also help us to get what? The other part of the answer. Okay, so this was first part of the answer, and this is the second part of what? The answer. Okay, so if we know the two answers involved, why don't we put them together? So that is why I've wrote it this way. So we are just going to add them and know what is going to be the actual answer to this integral question. Okay, u sine inverse of u minus, remember this one is already negative, so minus square root of 1 minus u squared. Okay, so we are going back to the x word. We are going back to the x word. Remember, I said the moment you are able to get your answer for a particular integral in a different word, quickly you have to go back to your u word, provided it's not what? A definite integral. Provided it's not definite. With definite integral, sometimes when you make substitution, the values involved, the numbers involved, you also have to change them. So whatever word that you reach, you can easily find your value by just putting, because you have already changed everything. Okay, so we know that u is equal to x squared. So we are just going to put them here. We are just going to replace them or put them back. So wherever we see u, we are going to write this x squared there. Okay, don't worry about this one. Okay, good. Now when we put x squared back, or when we replace u with x squared, this is what we are going to get at the end of the day. Here it was u sine inverse of x u, and you know that u is equal to x squared, so we are going to get x squared multiplied by sine inverse of x squared minus into bracket minus square root of 1 minus x raised to the power 4. You remember here it was u squared, and we know that u is equal to x squared, okay, so x squared times 2. When you replace u with x squared, is going to be x squared multiplied by 2 because there's already another 2 there. So that 2 multiplied by the other power to give us what? 4. So we will be getting x raised to the power what? 4. That is why here is 1 minus x raised to the power 4. Okay, now let's open the bracket. Now when you open the bracket, this is minus minus, that is nege nege po, that is what one of my teachers used to say, yeah, when I was being primary. You were solving fractions. Says, this one is nege and this one too is nege, so it's like nege nege. What you're going to get? You're going to get po. So when you forget it, maybe if you see it maybe somewhere and you don't know how to operate, just remember this one nege nege and then you say po. So that is why I'm making reference. So nege nege po. So that is why minus minus give us what? Plus. So the answer to this integral is x squared multiplied by sine inverse of x squared plus square root of 1 minus x raised to the power 4. So let's conclude everything. I said anytime you get your answer to a particular integral and you don't bring your plus c, you lose some marks or maybe you are wrong. I'm saying maybe because I don't know how the marking scheme are going to award marks. So maybe that place you are wrong, or maybe you lose marks there, and then where the plus C is included, maybe you get something there. I don't know how, it depends on the marking scheme. That is why I always say when you after getting your answer, make sure you add your plus C back. Okay, so let's add our plus C back to show that we are done. So therefore this integral is equal to this one. So this integral is equal to the whole of this one plus c, meaning we are done. All right, that's it. Please, if you like this video, kindly give it a thumbs up, subscribe and comment. Thanks for watching.